Good morning, everyone. Today, I will give the lecture about the spectrophotometry. So, I will give it in three different parts. So, from the introduction, the variables affecting the spectrophotometry, and also the calculation and instrumentation. First, I will tell you about the introduction of this spectrophotometry. Some chemicals have photoluminescence property. What is this photoluminescence? So photoluminescence, it's the property where a compound or chemicals excited by the light or radiation and then re-emitted the light or radiation, which can be either in the same or different wavelength. There are two types of this photoluminescence. We call it as fluorescence and phosphorescence. So I give you two pictures in here. Can you uh, determine which one is the fluorescence and which one is the phosphorescence? Okay, I guess all of you know about those pictures. The left one is the jellyfish and the right one is the stars. I think some of you already know these stars or maybe own this star at your room. So this star is advertised as a fluorescent star. Is it really fluorescence? No, it's not. It's a phosphorescence. So this star has the phosphorescence property, and this jellyfish is fluorescence property. What's the difference? I will tell you later. So if we talk about spectroscopy, we always talk about the radiation, and we know about the Pauli exclusion principle. What is this principle? So the spin of two electrons in the same orbital of an atom are opposite to each other or paired to each other. Because of the spin pairing, so most molecules exhibit no net magnetic field and are called as diamagnetic. In contrast, like the free radicals, which contain unpaired electrons, have a magnetic moment and called as paramagnetic. Molecule with an even number of electrons and all its electrons spin paired is called single state. So this is the single state. Both of the spin are paired to each other. It's opposite to each other. When one of a pair of electron of a molecule is excited to higher energy level, either a singlet or triple state is formed. What is singlet and triple state? In the excited single state, the spin of the promoted electron, the one who go out to the higher level, is still paired with the ground state electron. So as long as the electrons are paired, even if it is in the ground state or excited state, the molecule is in single state. We usually call it as S0, S1, S2, etc. But in triplet state, the spins of two electrons have become unpaired and are thus parallel. So this arrow is facing up and this is also facing up or facing down. So this one is also facing down. This excited triplet state has longer lifetime than the excited single state. And please take a note that singlet triplet transition is less probable than the singlet-singlet transition. And this is the example of the excitation spectrum. So A in here, the one in here is the excitation spectrum and the other one is the emission spectrum. So because the energy differences between vibrational states is about the same for both ground and excited state, so the absorption or excitation spectrum And the fluorescence spectrum for a compound often appear as approximate mirror image of one another, with overlap occurring near the origin transition. For example, zero vibration level of E1 to zero vibrational level of E0. There are many exceptions to this mirror image rule, particularly when the excited and ground state have different molecular geometries, or when different fluorescence bands originate from different parts of the molecule. This is the example of the spectrum of anthracene. Okay, and how is the activation of excited molecule? So, an excited molecule can return to its ground state by a combination of several states. So, these are two type of the process of the deactivation. There is radiation-less relaxation and radiation relaxation. What is radiation-less relaxation? So this is the activation without emitting any radiation or any light. For example, vibration relaxation or VR, internal conversion or IC, external conversion or EC, and then intersystem crossing or IX. There's also radiation relaxation like fluorescence and phosphorescence. So both of them involve emission of a photon of radiation. So it will emit the light or radiation. So the activation is always about the electron transfer from the excited state to the lower state or to ground state. For example, from S1 or T1 to S0. So this is the diagram, the Jablonski diagram, which told us about how is the excitation of the electron about the energy level. So in here you can see S0. So we usually call the ground state as S0, and you can see the lowest vibrational level of the S0 is drawn as a bold line, the bold line in here. So if you see, all of the state has the bold line of the vibrational energy level in here. So it's always in a bold line. And then the excited state of the singlet, we call it as S1, S2, and also the excited triplet state as T1. So the first, when a molecule is giving a light, is given a light by the radiation or the source of the light. So it will go through the absorption, so the electron will go up to the excited state, so it will be excited to the higher energy level, and then until one part it will go down to the ground state by the fluorescence, phosphorescence, or the radiation-less relaxation like internal conversion, vibrational relaxation, intersystem crossing, and also external conversion. So I will explain first about what is this radiation-less relaxation. Okay, first we talk about internal conversion. So it is sometimes called as radiation-less de-excitation because no photons are emitted. So it differs from the intersystem crossing in that while both are radiation-less method of de-excitation, the molecular spin state for internal conversions remains the same. So there is no change in the molecular spin, whereas it changed for intersystem crossing. So in internal conversion, there is the activation of the molecule from the higher state of to the lower state without emitting light. So for example, from S1, from S2 to S1, or from S1 to S0 to the ground state. It can also be happen if two state of energy level of the vibrational energy level close to each other, so it's overlapping. Like for example, in here, the lowest vibrational level of the S2 is overlapping to the vibrational level in S1, so it can go through the internal conversion from S2 to S1 in here. And then that's a vibrational relaxation. So it's the relaxation which is really fast, about 10 power minus 15 until 10 power minus 12 second. And it always happen in the same state. So if it's in S1, so it will go to the lowest energy level, lowest vibrational energy level in S1. And also in S2, it will just be in S2. So this vibrational relaxation will not be like go through the other state. So it will never be happen. So that the fluorescence always happen because energy transfer from the lowest vibrational energy level to the ground state. So this vibrational relaxation involves transfer of excess energy of a vibrationally excited species to molecule of the solvent. So if a molecule, if a electron is excited from this ground state to the very high level, to the highest level of the vibrational energy, so first it will go to the this lower vibrational energy and then get lower, 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 and until the lowest point of the vibrational energy, and then it will go through the fluorescence. So this fluorescence will never be happen like going from this vibrational energy and then go down. No, it will just go from the lowest point. And this vibrational relaxation is always drawn as the curvy small arrows like this. So if you saw something like this, and then this is the vibrational relaxation. And then we have intersystem crossing. So in this intersystem crossing, there is a conversion in the spin direction of the excited electron from singlet state to the triplet state. So if it's this is the state, in the singlet state it's like this, and then in the triplet state we will go to the other direction of the spin. And it can be easily occurred if the vibrational energy level of the singlet state is overlapping to the vibrational level of the triplet state. But take it a note that as I already told before, that this intersystem crossing is less probable to be happen than the other relaxation, like internal conversion and vibrational relaxation, because it's really less probable to be happen like this, the singlet state go to the triplet state. And then next, the external conversion. So this external conversion happen because of the electron energy transfer due to interaction between molecules. So it will go from the lowest vibrational energy level of the excited state to the ground state, like this, to the highest vibrational level of the ground state. And then we can talk about fluorescence. So after all of the radiationless relaxation, now we will have the radiation emission. So in here, the fluorescence is the activation from the S1 to S0. See, so it always go from the S1 to S0, not the S2 to S0. And it occurs in very short time, like I said before, so it's less than 10 power minus 5 seconds. It's really short. And if the radiation is stopped, so the excitation stopped, the fluorescence may stop as well. So it's really a very short time. And the energy absorbed by the molecule is equal to the energy emitted. This is about fluorescence. And the fluorescence wavelength is longer than the absorption wavelength. Okay, then how about the phosphorescence? Phosphorescence is a transition from the triplet state to the ground state, so T1 to S0. And it emitted light for longer time, so more than 10 power minus 5 seconds. Like the stars in your room, it will last for almost 1 hour or maybe couple hours. And then if the radiation stops, the phosphorescence may still occur. Like what happened to your phosphorescent star. When you turn off the light, it will still emit light.